Yeah. Hi. Good evening, everyone. Good evening, Professor, and good evening, TS. We are Team Cyphers, so we will be discussing about pharma IoT security, and my team members are Yash and Hemraj Patel. So we will see how we will secure pharma IoT sensors. Okay. So for example, we can take one example where we are shipping vaccines from one place to other, where those vaccines should be maintained, kept in some ideal temperatures, just like 30-degree temperature, 30 degrees Celsius temperature, and this temperature will be measured by sensors. But what if these sensors are compromised by any threat actors, and they will modify these values to 32 or 33, so all the vaccines will be destroyed soon. So this is the issue we will be focusing on, and we will say we will see the solutions how to not like we will not make this attack successful. Okay, so next slide. So these are the attacks that are possible from a threat actors, that is data eavesdropping. What if we can read the temperature or the data in eavesdropping, like whenever the data is there in the network, he can whenever the threat actor is there in the network, he can see that data if it is in plain text, so he can he will get to know the sensible data, and he can pass on this data to the competitors of that company, like other company. And we have message modification. Suppose we have not implemented any cryptographic algorithms, or we have kept weak cryptographic algorithms, they can change the readings and they can spoil these vaccines. Then comes device spoofing. So whenever if the threat actor is sitting in between the in network in between the devices, maybe he can spoof the network, or he can do like he can see the messages, all those things. Then we have replay attacks. So replay attacks is that if he sends the old valid messages again and again, so device thinks these are the genuine legitimate messages, and it will go and process the data. So these are the attacks we are speaking, and how we will stop these attacks. Okay, so we are going to next slide. Can you go to next slide? Yeah, so these are the security requirements we are going following the CIA triad, that is confidentiality, integrity, and availability. So first one is data confidentiality, where we'll be preventing eavesdropping; data integrity, where modification of the data; authenticity, preventing device spoofing; and replay prevention, that we will not send the data, the old data messages again and again. Efficiency, since the device, what is this? The sensors have very less computing power, so we'll keep efficiency in mind also. Okay, so next we are going to next slide for the other things. Yeah, so this is the first one is the implementation flaw. Suppose whatever the data moving between the sensors, so if it is moving in plain text, if it is moving in a plain text, so it is very problem, because someone is doing some attackers are in the network, so you can see that data. Suppose if you can see in the slide, it is 22.5, the temperature, pharma sensor one, the sensor ID, all those things, you can see those details. So it will be very dangerous if we are sending the messages in plain text. So how we can implement, how we can secure this? So that is the answer is in next slide. So we can go to next slide. So here we will do AES 128 encryption. So data will never go in plain text. Okay, so this is the solution for this. And next we are going to the second problem. So we thus, though we have encrypted, we have created the hash for the plain text, it will be never be secured, because somewhere in future, what if the attackers, or there will be some rainbow table attacks for AES 128. So what we will do again for the hashed value, we are doing encryption again with the MAC pattern. So the data will be never be given decrypted by attackers. Okay. So next we'll go for third slide. So here we have the hard coded keys. So this is one problem. What if all the encryption is happening between the sensors with using only one secret key, the static secret key? So what if the sensor itself is compromised and that key gets leaked? Okay, it will be again the problem. So what we are secret key can be leaked in GitHub repositories or something like that. So attacker can he will have the secret key now, and he can send his own messages. So how we'll solve this? So that answer we have in next slide. So we are using DefiElement. So once we are using DefiElement, whenever we are using DefiElement for this problem, the secret key will be never be sent on network, and it will be computed through two public keys of those devices. So this is how we have stopped the attack of compromising the secret keys. So now I'll be passing on the thing to Ash for further explanation.
So let me explain how DCLM works. A simple overview. Imagine three parties: Alice, Bob, and someone, and Eve, who's an eavesdropper who is listening in. We start with a public color yellow. Everyone knows it. Eve knows it. This is a public parameter. Alice picks a secret color red. Only she knows this. She mixes a yellow and red and gets orange. She publicly sends this orange paint to Bob. Bob picks a secret color blue. Only he knows this. He mixes yellow plus blue and gets green. Now here's the magic. Alice receives the green paint. She combines it with her red, gets brown. Bob also receives Bob, who has received orange paint, combines it with secret blue, gets brown. They both have the same color brown, their shared secret. But Eve, who can only see yellow, green, and orange, even if she tries, she can't unmix these colors. She can't figure out what brown is. This is the beauty of DeFi. Two parties derive the same secret, but an eavesdropper can't compute even if they have all the public exchanges. Here is a 5-step on how this entire project works. Let me walk you through it. Sensor connects gateway via TCP connect. Connection opens, but no data flow yet. Gateway generates a random key like A, like Alice is secret red. It computes the public value A, which is g to the power A mod B, and sends it to the sensor. The sensor then generates its own random private key B, computes it, g to the power B mod B, then sends it to the gateway. This is where the magic happens. Both parties independently compute the shared secret, which is g to the power A times B mod B. That's the gateway computes this value and the sensor computes this value. They get the same exact value S without ever sharing the private keys A and B. An attacker with the shared secret cannot compute S without knowing either their own A or B values. Both parties feed the shared secret S into a HMAC-based key derivation function. This industry function stretches one secret into two independent keys, which is one AES 128 encryption, another HMAC SHA-256 authentication key. Key point here is that the key handshake happens before any data is sent. If an attacker can't complete the handshake, which if he doesn't have the DH values, they can't communicate at all. Attacks are blocked at layer 1. Let's talk about perfect forward secrecy. Looking at these three connections, each one shows different encryption and MAC keys. Connection 1, AES starts with whatever the value is. Connection 2, completely different AES key. Connection 3, again, brand new keys. This is perfect forward secrecy, one of the most important concepts in modern cryptography. Here's why it matters. Suppose our sensor gets compromised tomorrow, an attacker captures the device, extracts every private key, steals all cryptographic material. Sounds like a total disaster. But here's the catch. We have never stored the old shared secrets. The DH parameters are ephemeral, meaning temporary one-time use. So even with full device compromised tomorrow, the attacker cannot decrypt today's traffic. Signal uses this, TLS 1.3 uses this, many enterprises systems require it. Compare this to the initial approach with single static key. If the key is leaked on GitHub, all traffic could be decrypted forever. So what I want to say here, or what I want to emphasize, is that we use 5 layers instead of just encryption or just MAC. Layer 1, DH key exchange. This is the breaker switch, no handshake, no communication. All 5 attacks we're about to demo are blocked because an attacker cannot complete the DH key exchange. The second layer, if somehow the attacker gets through the first layer, the second layer, Cypher text is unreadable, even with plain text in front of you. You can't reverse the encryption. If somehow the attacker breaks layer 2, the next layer, HMAC SHA-256, this detects modification. Change in one bit is the change in the entire Cypher text. The gateway will immediately reject it. If somehow gets to layer 3, then we have sequence numbers. Each message has its own incrementing sequence number. Replaying an old message means sequence is out of order. If somehow the attacker breaks through layer 4, we have timestamps. Messages arrive within 60 seconds of device's clock. Sale messages are rejected. Point is, an attacker has to break all 5 layers to hack the entire system. Now, let's talk about the actual code. This here is the Python code implementing Diffie-Hellman. Ephemeral keys. Every call to generate underscore key pair creates a brand new random private key. We never reuse keys. This is perfect for perfect forward secrecy. The HMAC based key derivation, we don't use this raw shared secret S. That would be cryptographically weak. Instead, we use HKDF SHA-256, which is NIST recommended key derivation. No pre-shared secrets. The entire DH handshake is zero configuration, no hard-coded keys, no PKI setup, no certificate exchange. Both parties independently derive the same secret using only public parameters. The 2048-bit security, we use RFC 3526 DH parameters recommended. This is the standard size used in production, TLS, OpenVPN, etc. This is the actual sensor simulator. This is what will go on an actual actual IoT sensor. This is the pipeline. Encrypt then MAC, as we explained before. We encrypt the plain text first. We compute HMAC over the resulting ciphertext. This order matters, as MAC then encrypt is vulnerable to padding Oracle attacks. Sequence tracking. Before encrypting, we increment a sequence number. This number is included in the plain text before encryption, so it's authenticated by HMAC. Replaying an old message means replaying the same old sequence number. Timestamp freshness, we added a Unix timestamp when creating messages. This gateway will verify the timestamp within 60 seconds. Old captured message won't replay. Fernet implementation. We use a Fernet encryption, Fernet Cypher library for implementing the AES HMAC implementation. For authentication, in one convenient function, it handles IV generation automatically. This is the secure gateway. The gateway is the verification point. The order is MAC first. Before decrypting, we verify the HMAC constant time comparison. This prevents timing attacks where an attacker modifies the MAC and measures how long verification takes. Decrypt after MAC verification, which means only if the MAC is valid do we proceed with the decryption. This prevents padding Oracle attacks, as I said before. Per device sequence tracking. The gateway maintains expected sequence numbers for each sensor. When message arrives, we check is the sequence number higher than we expect. If not, it's a replay rejected. Timestamp window. The timestamp window inside the encrypted payload must be recent, as I said, 60 seconds. All checks are layered independent. If any check fails, the message is rejected. This is the sensor network, the network sensor with the Diffie-Hellman. This class handles the sensor side of network communication with TH integrated. Handshake before data. When the sensor connects, it immediately sends and receives DH public keys. No data flow happens until this is done. Per connection, ephemeral keys. Each time sensor opens a TCP connection, it generates a fresh DH key pair. Different connections, different keys. If one connection compromised, connection 2 is unaffected. Automatic encryption. The encryption is transparent. The application layer just calls send secure message payload, a constant that you'll see here. The encryption and MAC happen internally. This is important for usability and preventing mistakes. Error handling is done if the gateway doesn't respond. Timeouts happen. Connection failures, invalid JSON, passing, all handled gracefully without exposing cryptographic detail. The gateway network PI. The gateway is the server side. Key architectural points are threading. The gateway uses multi-threading to handle multiple sensors simultaneously. Each sensor connection runs its own thread. Mutual key exchange. Both parties exchange and verify public TH values. This is mutual authentication. You can't fake it without completing the HMAC. Per connection isolation. Each thread has its own encryption MAC keys derived from DH threads. If one sensor is compromised, other sensors are unchanged. Statistics tracking, this helps us to monitor for attacks. A sudden spike in rejected message could indicate an active attack. These are the attacks that we will be focusing on. The first attack modification. This demo runs an actual attack trying to modify temperature value in an encrypted packet. The attack logic is intercept a legitimate encrypted message, flip bits in the ciphertext, send the modded packet to the gateway. What the code shows is HMAC computation prevents forgery. Attackers cannot create a valid MAC without the key. Constant time comparison prevents timing attacks. All or nothing, which means that changing one bit makes the entire MAC invalid. There's no partial success, no false positive. No false positive means legitimate messages still pass all checks. The gateway receives, the point of this demo is to show that the gateway receives the modified packet, verifies the MAC, finds it invalid, rejects the message, the attack fails, and a log is generated. Device spoofing. An attacker tries to send a message impersonating a sensor, pharma sensor, whatever it is. Number 1, number 2. What happens is DH prevents MITM. The attacker can't complete the handshake, so they can't derive the correct keys. MAC prevents forgery even if they guess at an encryption key. Even if they guess an encryption key, they can't provide us. Even if they guess an encryption key, they can't provide us valid HMAC without the real key. Sequence number blocks any replay attacks. If they try replaying an old message, the sequence number is wrong. Again, no false positive. Real message sensor passes all checks. The gateway state machine expects a DH handshake before accepting data. The attacker skips the handshake and sends spoof data directly. Connection is rejected immediately in such case. Packet replay with Netcat. This is interesting because we are using Netcat, a raw TCP tool with no cryptographic awareness, to replay captured packets. The attack is capture a legitimate encrypted message from a real sensor, wait for a new connection to start, replay that old message using Netcat. Why it fails is old packets were encrypted with old DH keys from a previous session. Current session has different DH keys, old packets MAC is for the wrong keys. Immediate failure. Sequence number tracking. Again, in all attacks, if the sequence number is not greater than the first one, then the packet is simply dropped and no attack is possible. MITM with SCAPI. With powerful packet sniff packets from the wire, modify them at IPTCP, retransmit modified packets. What the attacker sees is the gateway's DH public values, sensors DH public values, and encrypted payloads. To break it, they need to complete the handshake without solving discrete log. To forge valid HMACs requires the shared secret which is impossible without the DH keys. And to break it, they also need to modify the payloads meaningfully, which would break the MAC. Why this fails is because DH provides authentication, the handshake is mutual, you can't complete it without being one of the legitimate parties. Shared secret, why it also fails is shared secret not compromised. The attacker sees the public values but cannot compute the G to the power A times V. MAC verification, and why it also fails is MAC verification. Obviously, MAC provides modification. If the packet is changed, MAC provides all modification, and the MAC then changes, which stops any integrity attacks. This is the strongest attack demo. This is the strongest attack in the demo we have. Arun, can you pause them? Here's the actual attack on how it works. You just run this script. Make sure you have all the files with you in the same project folder. You run the attack. This is the gateway network. Once this has started, this IoT devices send data over this gateway using this gateway network. All of this is happening at localhost, as you can see here. Once I created a small script that runs all the attack demos through one Python script. So the first attack message modification. This, as you can see, the attack is blocked by Diffie-Hellman key exchange. The replay attack we created another simple replay attack demo. This isn't as advanced as the other with SCAPI. You can see all of the key exchanges have failed. If the attack had succeeded, the connection would have been open. They would have been able to connect with the gateway network. Then the device spoofing attack. Again, spoofing blocked by Diffie-Hellman. Attacker cannot complete handshake without proper keys. Again, closed because it's not perfect. The Netcat replay attack. This is an eavesdropping attack. This will take data. Again, failed. Replay attack blocked by Diffie-Hellman, as you can see. Then we have the MITM SCAPI attack. This is the most advanced attack because this uses a real-life tool used by many adversaries. All of these attacks, as you can see, are blocked by the gateway network. So no connection from this fraudulent IoT sensor will go to this one. Arun, pause.
So it's time to recap the whole project and why our project stands out. It is because it solves a real-world problem in pharmaceutical supply chain where temperature data must stay accurate and protected all time. We demo a complete security system that defends against eavesdropping, message modification, spoofing, MITM, and replay attacks. All of these threats are real in IoT systems, especially when shipping vaccines or other sensitive medical products. Another reason this project is strong is that we only used industry standards cryptography. We didn't invent anything or rely on custom formulas. Because of that, our design is reliable, follows best practices used in real companies, not just academic examples. Overall, our project is strong because it not only meets the requirement, but goes above and beyond by adding secret key exchange, perfect forward secrecy, and multiple layers of protection. So that's all for this project. Thank you all.
Hi everyone. Good afternoon, Professor and TAs. So this is Team Cypher, and I am Arun Channaraju, and my teammates are Hemraj Patel and Yash Valsangkar. So we are showing our ID cards. So NYU ID cards. This is our ID card. And now let's continue with the project. Thank you.